Hello. Okay. I guess I can start. It's a very crowded room. Thanks for attending my session. Um, so please don't forget to rate the sessions. Okay. Let's get going. So today I want to talk to you about implicits. Well, the background for the talk is a bit that many Scala users encounter implicits after a while using Scala. Not always they know what's going on under the hood. So the talk is for those people that want to know more about this and to take away the magic around it a bit. So today we're going to talk, I give a small introduction about myself. I'm going to talk about implicits, how they are resolved by the compiler. And we'll look at an example of type classes and how implicits are really powerful here. Okay, well, my name is Soethout. I work at ING Bank, where much of my time goes into training my colleagues in reactive and functional programming. I come from a Haskell background in university. And since last October, I'm also a Lightband certified trainer, and I teach the course to my colleagues. Next to that, I had the opportunity, ING gave me the opportunity to also pursue a PhD, and I'm now working on going from declarative specifications to actually generating runtime systems based on reactive. If you want to know more about ING, talk to me or talk to some people at our stand just outside here. Well, let's go into implicit then, because that's what we're here for. So a bit of background. Oh, that's too much. A bit of background. It's basically, implicits enable you to actually use values without explicitly referencing them in your code. And this allows you to write less code and leave things out, actually. So if we look at OO, you have the is-a and a has-a relation. So for example, a cow is an animal, and an animal has a name. So that's more of the member operation. And implicits add something on top of this. Is viewable as a, and you can imagine that, for example, you can look at a cow as something you can hang your coat on, for example. So this is like a really different view than that is separate from what the cow was originally created for. And what this allows you is to actually write very small models and interfaces, and then add rich views on top of that are loosely coupled from them. So let's take a look at some examples of implicits that you might know. So here we have an akka example. So we have this tell message here. That's the bang operator, that you use to send a message to another actor. And in the definition, you see a second parameter list, implicit sender here. So this means that that you can specify the sender here, or you can leave it out, and it will put in a sender from the scope, which is in the normal use case is the current actor that you're in will be the sender of the message to another actor. Another example is the bottom one, the future. We also here have an implicit execution context, and this execution context takes care of scheduling all the futures on the different threads under the hood. And you can put a different implicit in here to actually change the behavior a bit. Another example, the standard collections library of Scala. Here we have the traversable ones, which is like a super class for most of the collections, and we define a sum operator there. And for any type for which there exists a numeric b that is being passed in implicitly, we allow this sum operator to work. So for example, we can use it down here for a list of integers, and it will work. So this is actually a type class, which we'll delve into a bit later as well. Another example, this is more involved. This is the old Finagle client builder. Finagle is the RPC framework, and you can configure it. You have this client builder here. So let's walk through it. We have a client config evidence, which has 3 type parameters. Then we have the actual client builder. I left out some code, obviously. Which, when you want to call the build function, it requires an implicit to be there. And it needs to be of type client config evidence with the hash cluster, the hash codec, and the hash connection limit. This means that all of these type classes need to be, all of these types need to have the correct value to be able to actually call this build method. So what it ends up for the user of the library is something like this. So you create a client builder, you configure the codec, you configure the hosts, but I don't configure the connection limit yet. Now, if I try to call the builder at compile time, it will already throw an error because an implicit is missing, and the custom error message is showed here. So the builder is not fully configured. Well, we still need the hash connection limit. So these are a couple of examples of what is the power of implicits. So we see that there are lots of use cases already here. We saw some examples, but there's of course more. It is very much used in the domain of DSLs because you can extend existing types from the Scala library, like strings and integers and those kind of things, to write powerful DSLs. You can use them as type evidence. We already saw an example here for the Finagle client builder, and also a bit for the .sum on the collections library. Because you can leave things out, they reduce the verbosity of your code. They allow type classes, which is a way to extend libraries or code that you do not have any control over, and it's quite powerful, and we'll see an example soon. And you can even do things like a simple dependency injection, because depending on which implicits are in scope, other dependencies are being used, and this is all checked at compile time. And for the last item, this is really where the type classes shine. Of course, it sounds very great, everything, but there are some things you need to be aware of. If you just look at some Scala code, and there are implicits involved, sometimes you cannot really see what the code is doing by just looking at the code. You really need tool support like IDEs that signal where implicits are being used, for example. And this is also where the magic of implicits come from, because you can no longer, by just looking at the code, see what is happening. So for example, IntelliJ is really helpful here. You see the underline underneath a value if an implicit conversion is being used. And IntelliJ can also help you in pointing you to which implementation is actually being used underneath. Automatic conversions, that's also one of the features that came into Scala. Martin actually warned us about this already yesterday in the keynote, that this is a feature that can easily lead to problems. For example, if you automatically convert certain values to other values, the semantics might change and might do something that you not want. For example, if you automatically convert doubles to ints, you lose your precision and you don't see anything in your code and you don't know where the bugs are coming from. And of course, the last point, do not overuse implicits. We already saw the blog of Lee Howe in the keynote as well. The principle of least power. If you can achieve something you want to do with a less complex feature, use the less complex feature, and only use implicits when you really need them. So enough theory. Let's look at some Scala code, how this is actually being used. So, yes. So what we are looking at now is represent. So it's a thing to present slides inside of the REPL. So I think it's really cool. And to keep you with me, I'll explain a bit how it works. If I press N here on the command line, I will go to the next slide. That's pretty obvious. If I do R, I actually run the code that is on the slide, and we'll see the output underneath here. So what I did here is I defined a method with an implicit parameter, implicit I int, and we'll just return it to see what's happening there. We can call it like a normal method by doing nothing with the implicit. Now, if we create an implicit val, some int, it is available on the implicit scope. And what happens now is that we can actually call the method, and it will find the int for us. So what is happening here is that give me an int normally would not compile. Because we put the implicit keyword here, it knows that it should try and find an implicit with the correct type in the implicit scope here and fill that in for us. And another way to get the implicit value, you might have seen this in some libraries, is implicitly int. So this means just give me something from the implicit scope of type int. Actually, the implementation is exactly the same as our give me an int here, but then for the generic type. And this will also work. It will give us the 42. So what is actually happening under the hood here? So I've wrapped this method we already created in this method here, some call. And actually, if we call Java P, we can look inside the bytecode. So what do we see here? Here we see some call being defined, and we see some instructions on the JVM. And what we see is that the third in line is get some int, and then give me an integer, which requires one integer as parameter. So what happens here, this method is being called, the value is being put on the stack, then the next method is being called, so the first argument will be the result of some int. So what you see here is that there's no implicit magic anymore. As soon as it is compiled to the bytecode, it's just plain method calls. So the compiler takes care of the implicit resolving and everything, and then the bytecode is optimized like this. Okay, so what happens if we define another implicit val with the same type? So if I run this, we would have two integers in the implicit scope, one with 42 and one with 1337. If we try to run this and call the method again, the compiler doesn't know which one to pick because there are two, and it will actually warn you about this. So ambiguous implicit values, they have some int and another int as well. Let's take a look at implicit conversions. So this is the scary feature, basically, that you really shouldn't overuse. If we define a simple method here, make string, which takes an int and just prints it, well, not print it, it converts it to a string with some extra string around it. We can just call it like a normal method as we're used to, nothing special here. We also create some model object for us, for example, here balance with one member amount, and create a value for it. Now, what we would like to do is actually call make string on this case class, but well, this will not work because it expects an integer and we give it a balance. So what we can do is define an implicit conversion. So we signal this again by using the implicit keyword. We give it some name, it doesn't really matter what, but this is the naming convention they use in the Scala compiler. Give it one parameter of balance of the source type and then the target type. And for this implementation, we just take out the amount of the case class. Now with this defined, the feature warning is actually there because the compiler already warns you that you should be really careful with implicit conversions because it can convert values and maybe you don't see it. So now if we call make string on this balance, it will work because what is actually being generated under the hood is make string. It doesn't compile like this, so it will try to look for an implicit to make it compile. So we get the balance to int being called on our balance value. And yeah, it's the same. So this is what the compiler does for you by using the implicit conversion. You might have seen something about Java conversion and Java converters. Well, a use case for this would be, for example, if you have a Java list, but you have a a Scala method which takes a Scala collection type instead of a Java collection type. So we define this. Now we want to call it on the Java list, and this doesn't work. Well, you already see the pattern here. We can use an implicit conversion. But in this case, the standard library actually contains some conversions for you, which I imported here with the wildcard import Scala collection Java conversions._. And now we can actually run it. Because what happens now is it tries to find, the method here requires a sequence of int. We pass in a Java list. It does compile, so it will look in the implicit scope, is there something that I can use to make this actually compile? And yes, it is defined in here. But this is, of course, a bit scary, because you don't know what is happening here. You might have a conversion from a list to a stream, so the semantics change. So in this case, you might want it, but if you in the same file want to do some more, then you get an implicit conversion, which can lead to very strange bugs. So a better way is to use the Scala converters. And in this case, you import them as well, like this. But now it only enriches the Java type here. So this is also an example where an external library is extended with functionality you might want. So in this case, you can now call Scala on the Java list. It very clearly signals it to you as the user what's happening here, that there's actually a conversion taking place. But still, you don't need to write some enormous code where you loop over the first one and fill up a second Scala collection type. Well, implicit views, that's another powerful feature. So to set up here, I create a string wrapper class, which has one member, a string, and we define a method on this quoted, which just puts extra quotes around the string. And we can, of course, use it by instantiating it and then calling quoted on it. But wouldn't it be nice if you can actually do something like this? You can just do dot quoted on the string directly. Yeah, this will not work at the moment because quote is not a member of string. Well, you already see where this is going. We can, of course, write an implicit conversion again for this. So we have this implicit wrap string, which calls the string wrapper constructor for us. Again, it gives us a warning because it's a feature you should not misuse. And now we can do this. Okay, well, that's great. So this is like you can extend in this way some types you do not have control over by lifting them to your own wrapper type and then adding methods on it. You also have view bounds in Scala. They still work, but they are deprecated, but I just want to show it to you because you might encounter it if you're reading some source code. So what do we see here? We have some type parameter, and we have this view bound operator on it. String wrapper, that's the type we just defined. And it takes one value of the type. And suddenly we can call t.quoted on it. This actually works. And this is because now, because we put it in this type bound, we actually say that, that there should be a string wrapper of t for this type t in scope. And then we can use it as if it is also instance of string wrapper t. So what we see here in the actual definition down here is that the view bound is actually converted to an implicit conversion here. So the sum def using quoted strings now takes an extra parameter list with implicits that supplies us with the conversion function. And yeah, as you can see, this works. Yeah, I just explained this already. So the type bound is syntactic sugar for a view of t to string wrapper, which is shown here as this function, implicit function. And this works. Yeah, of course, we haven't defined a string wrapper for integer types, so this will not work, and the compiler will actually tell you why it isn't working. No implicit view available from int to string wrapper. And of course, if we do supply it, then it will work. What we see here is that instead of using the the method with the single parameter in the argument list, you can also define it as a function, because Scala will do the automatic conversion for you, and this works. So the magical keyword here is implicit to make it available in the implicit scope. Another example, you might know this from the standard library as well, 1 to 10. If you run this, you get a range from 1 to 10. Of course, the to method is not defined on integers. So what happens here is that there is something called rich int in the standard library, which does define the to method, and there's an implicit view available that is automatically in scope by using predef. And we'll do the conversion for you. Implicit class. So this is another way where you can write the implicit keyword in Scala. So we have a simple domain here, balance with an amount. And we want to write up here minus balance. So assume for now that the balance is defined in a library or in a different file where you do not have control over, and you want to have some kind of functionality like this. This will not work because we don't have the unary underscore minus member on balance. So this is just a way of writing in Scala the prefix operator. Now we can make a wrapper class again, but instead of making a wrapper class and defining an implicit conversion that will lift your type to the wrapper class, we can also use an implicit class here. And this works because we supply it with one value parameter. Then on the rich balance, we define the method we want to have. And then, if we try to do minus balance, it will actually work because it will see the implicit class. It knows it can lift it to this type, to this rich balance, and we can call the unary operator, the minus. So in this case, implicit class is used to extend a library, basically. And this is very simple examples. They can, of course, become more involved with more complex types. Okay, let's go back to the slides for now. Okay, so we saw some examples here of implicits, but how are those implicits resolved? We only saw some very simple examples where I just defined the implicits in the same code as the values where I was using them. Well, I found a blog where Martin Oderski actually explains the reasoning behind this, how the implicit lookup works. And it's basically this. It first looks for a simple local name, which it can use to make it compile. And then, if that doesn't work, it will start looking in the implicit scope, and it means in the companion object or package object of any of the types that is involved in the current statement or expression you're writing. So, for example, if it wants to have an integer and you give it a string, it will look in the companion object and types of int and also of string. And also, if it cannot find it there, it will look in the hierarchy of supertypes and supertraits of int and string. And so, the reason behind this is that when you're writing a library and you want to provide some sensible defaults for your clients, for the users of the library, you can put them in the companion object or the package object of your library. And if the user actually wants different behavior than your sensible defaults, he can make sure that in his local scope there are implicits of the correct types defined there or imported there. So let's take a look at some examples again. Here we are. So this is a nice part. So let's first go through the slide. What I did here is I created a simple case class with a simple content string in there. We create also a companion object where we define an implicit value of the type case class with this nice explaining string. We have another object explicit and another object wildcard. And then we define the find case class, which takes one implicit parameter of case class just to show what it will resolve. So let's make this part a bit more interactive. So what do you guys think that this will result in? So If you think it will print the part defined in the companion object, then raise your right hand. If you think it's part of the explicit, raise your left hand. And for the wildcard, just raise both hands. So what do you guys think? I see mostly left hand, one right. Let's see what's happening. It is the one defined in the companion object. This is because at the moment there is nothing in scope with a simple name in the local scope. So it will start looking in the companion object of the types that are involved here. And in this case, it's case class. Now, what happens if we do this? So what did I change? I define a local case class here, also implicit. So we need an extra hand for this. So companion object, explicit, wildcard, and the local one. What do you guys think? Yeah, amazing. Let's see. Yeah, it is the local one. Good job. Now we do another one. So here we see the wildcard import. That's why it's called wildcard. So we have wildcard._. Same holds, companion object, explicit, wildcard, and that's all. Yes, looking good. Let's see. It is the one in the wildcard, correct. Now we have the explicit import. What do you think, what will happen here? So, companion object, explicit, wildcard. I see some companion objects, I see also some explicits. So let's take a look. It is the explicit one, and this is because by doing this import, actually the implicit file comes into scope with a very simple local name. So because we can access it with this name, because of the import, it will pick that one, and it will first look in local scope, and then only will start looking into the companion objects. And now we have another one. What happens if we both do the explicit import and the wildcard import? What do you guys think will happen? So companion object, explicit, wildcard. So I see some wildcards and some companion objects. So this is a bit of a trick question, because what will actually happen? Ambiguous. I didn't give you the options, I'm sorry. Well, because now both with the explicit import and the wildcard import, they become available with a simple name, so it cannot choose anymore. Now this is just another example. What I did is I inserted this trait parent here, which is actually the parent of the companion object of the case class. And this is just to show that it will go looking into supertypes of the companion or of the types involved in the computation as well. So in this case, we will actually get the implicit being resolved from the supertype of the companion object of the case class. Okay, so this is another example. Let's go back to the slides for a bit. So, yes, type classes. Well, this is a very powerful feature that's actually being driven entirely by implicits when you want to implement them in Scala. But first, a bit of background. Type classes actually come from the programming language Haskell, and they need them there because there's no subtyping in Haskell. So you cannot, by inheritance, override implementations or overload functions. So they invented type classes for this. But that doesn't mean it can only be used in Haskell, and we can actually implement them in Scala as well using implicits. And mainly it is used to extend existing libraries, so types you have no control of, that you want to add some functionality on. So for example, we see here the numeric T trait in the Scala collections library, which is used to how to say this, to group a couple of operators that should work on this type T here. Of course, if you want to, for example, use this on on a collection, you want to have the plus defined on something, you can do it by inheritance, by creating some interface, summable or something, and then implement that on every type you want the plus function to work. But this doesn't really scale, and you need to change all the types for which you want this to work. To get a little bit more feel about this, we'll take a look at an example for JSON serialization. So first we'll look into the naive implementation using inheritance, and then we see how type classes can actually improve this for us. Okay. No, other way. Okay. So we have a very simple trait here, which defines this toJSON string. I just use the type string here to represent JSON for now, to keep it simple. But in real world, you probably use something more involved here. So let's run this. Now, what we can do is define our model. In this case, we have an account case class, a payment case class, and a person case class, and they all have some fields. And then we extend the JSON serializable and implement the method we need to. Well, this is just a very crude implementation now, of course. Let's run this. It will work fine if we create an account. We can call toJSON string on this. So, well, this could be an approach to writing JSON serialization. It works. I actually made a mistake. Don't know if you actually saw it. In the implementation of the JSON, I made an error. I used the wrong word. So what we see here is that there's actually lots of manual work, lots of writing. You can easily make mistakes, and your whole model class is basically cluttered with all this JSON serialization code. And imagine wanting to implement more interfaces, it becomes very big and unreadable. So let's look at the type class approach. So what we can do here is we can first define the model up front, create the case classes, some values to play with, and then look at this as a separate library that we do no longer have control over. But we still want to implement JSON serializability on this. So let's walk through this slide. We have a JSON writer here for type T, and if we have a JSON writer, we can actually serialize a value T here of type T to a string if we implement this method. So what we can do is we can create a JSON writer for strings, and then given input string, it can actually convert it to the JSON type we defined. Same is for big decimal. We create a JSON writer for big decimal, and we implement it, and we see here that I actually use the JSON writer for strings here, and I summon it from the implicit scope by using implicitly here. And now I can use this trick by converting the big decimal to a string, and then calling the JSON writer for string on it to put it in quotes again, to make it JSON compliant. What we see here is that I actually define everything with implicit keyword here. So these JSON writers for string are now available in the implicit scope, if I run this. So now what we can do is we can also define a JSON writer for our account. I reuse the string and big decimal JSON writers, which are defined on the implicit scope, and therefore I can call them up like this. And I write some value here to JSON. Yeah. So if I run this, we'll see if I grab the JSON writer from the implicit scope for the account, I can actually use it to serialize my account here. Of course, it's still quite a lot of boilerplate. You have to summon all the implicit types for all the fields you have, and then use them to do the actual serialization. And if you use it in the end, you still have to write, give me this JSON writer, and then I can use it. It would be much nicer to just be able to call toJSON on our model types here. Well, we saw this pattern before, right? So, well, it will not work now because we don't have it yet. We can use an implicit class here to lift our model type to something that is JSON serializable, and then use it. So what is happening here? The first part is being used to enable the lifting of the type. So the implicit class requires a serializable here, but it can only do that if it can find an implicit serializer of JSON writer for this type that we're currently lifting in the implicit scope. And then, if we have those ingredients, we can very easily define toJSON because it's just using the serializer we got in, calling the toJSON string on the type we got. And now, this turns out to be enough to be able to do myaccount.json. So what is happening here? I try to call myaccount.toJSON, so the toJSON method will, well, in a normal case, will give a compiler error because it's not a member of my account, so it will try to look in the implicit scope, is there something that I can convert it to, which will make this compile. And it can find it, because it finds this JSON serializable. Fortunately for our type, we also defined the JSON writer, and therefore it can actually do this conversion for us. Now, some more generalization. So what I did on top here is I created a JSON writer, which is, well, in this case, it's not the companion object, but if you would define it at the same time as the trait, it will be, which simplifies the way of thinking about JSON writers. Because the only thing a JSON writer does is actually convert the type to our JSON type here, which is string. And what we do is we instantiate a new JSON writer, and we fill in the implementation with this. So this is just to be able to write things a little bit smaller. Now we can define a JSON writer for map. And maps are really usable for JSON because, well, most of the times we're talking about key-value pairs when using JSON. So this is quite a natural abstraction for JSON. I use some special syntax here, which is similar to the view bounds we saw earlier. These are actually called type bounds. So what this means is that for our key type, for our map, we will only allow this method to be called if there is a JSON writer for this key type. What we can see here on the bottom is this is the exact same signature. It's equivalent. So we get an extra parameter list for our JSON map, and one will with two values, one for the key and one for the value. So there should be a JSON writer for the keys and a JSON writer for the values. And if that is the case, we can actually in the end return a JSON writer for the map of our keys and values. The implementation is quite straightforward. We actually loop well, it's not really looping, of course, but with this for comprehension, we walk over our map, and for the key we do the toJSON, and for the value we do the toJSON, and this will work. The toJSON here will work because we have the implicit class defined we had earlier again, and there are JSON writers on the implicit scope for both of these types. And then at the end we join everything up with the commas in between. So let's get this in scope. Note that all of these, or actually this JSON map is again defined in the implicit scope. Now, on the bottom line, we can actually use this on maps. So what we have now is that if we want to write a JSON writer for one of our custom objects, we can actually reuse this map JSON writer. So we create a JSON for our payment type in our model. We reuse the apply method on the companion object of JSON writer, where payment is passed in, and it is enough to just convert everything to this map. And because we know how to serialize maps, we can call toJSON on this. I cheated a little bit here, because what I did here was actually converted the amount to a string here, so it will be map of string, and otherwise it would have been map of string any, because the first supertype of big decimal and strings is any, and we don't have a JSON serializer for any in scope. So, but of course you can fix it with lots of type level magic. But for the example, this is good enough, I think, to illustrate the point. Now we can actually have our payment from our domain model and just serialize it. Yeah, so you can, of course, improve on this again. because I still have to write from here and to and all my fields. And because case classes is actually a sum type, we can do some generic operations using shapeless and everything to get these field names out and generalize this a bit more. But it's basically extending on this idea, but I won't go into this today. This is what I want to show for the demos. So let's go back. Yeah. So let's take a look at the time. Okay. So let's wrap up for now. So I hope I've shown you that implicits allow for quite some powerful things. You can write expressive code. You can create DSLs. You can extend libraries that you do not have control over, even the Scala standard library. And you can even do some rudimentary dependency injection with it. Take care with implicit conversions, because they can lead to unexplainable behavior by converting things to other things which don't share the same semantics. Maybe they iterate over a list while you don't even know it, and your performance degrades. But your IDE can really help you spot these kind of things. Yeah, what I want you to remember about the precedence, so how is the implicit resolved? It will first look local with a simple name. If it cannot, it will look in the main object of the types involved. That's the basic rule that you can really help you when you want to start debugging these kinds of things. And we looked at type classes and saw a way where we can actually extend our model here in a non-intrusive way, and we have really nice loose coupling between the model and the things we add on top of it. This was actually what I wanted to share with you today. Are there any questions? There in the back.
How does it work with type aliases? If I have type balance equals int, for example, and then a function that needs an implicit balance parameter, and only have an implicit int value defined, will it find that int? Will it resolve it?
Actually, I don't really know, but we can of course just try it out. So you say we make a type alias. I think this is the syntax. So we have my string is int. Oh, not upt. And now we want to define a method that does something with. No, wait. So use my string in implicit def as. Not sure if this is going where I want it to go, but let's see what happens. What's going wrong? Oh, yeah, of course, the other def. Okay. Use my string. And I guess you want to have something of type implicit int now in scope. I think we already have that. Oh, that's not good. Wrong one. Okay, so let's define this again. Why is this not working? Oh, the type again. Type, we can define it. So now if I bring an implicit val in scope, implicit val e of type int is 42. And I want to call use my string, it will actually work. So here it equates the, well, it actually sees that the my string is an int, and it can also use values of type int. Of course, if I do implicit file my string of some other value, and I call it, then it will use that one because it's more specific here. So there's no ambiguous implicit here, but that's it. I hope this answered your question a bit. Thank you very much.